This is Rosen, section 5.1 on mathematical induction. We're going to do a few example proofs by mathematical induction. As mentioned earlier, induction doesn't itself help us come up with conjectures. So let's do one of just a conjecture. We're going to conjecture a formula for the sum of the first n positive odd integers, and then we'll prove it using induction. So the sum of the first one odd positive integer is 1. The sum of the first two odd positive integers is 4. The sum of the first three odd positive integers is 9. The sum of the first four positive odd integers is 16. The sum of the first five positive odd integers is 25. And so it would seem natural to suggest that the sum of the first n positive odd integers is n squared, and that would indeed be our propositional function that we want to prove for all n. Or we could state it like that. So to prove that statement for all n, we'll use mathematical induction, and we start with the basis step. The lowest value on our list, we're looking at positive odd integers. So we're doing induction on the number of odd integers. The sum of the first one odd integer is true because 1 is equal to 1 squared. So n is the number of odd integers in order. And the nth odd integer can be written as 2n minus 1. All right, so let's show that the inductive hypothesis pk implies pk plus 1. That's our inductive step. We'll state the inductive hypothesis. We're going to assume it holds, show pk plus 1 holds. Here's the inductive hypothesis. Sum of the first k positive odd integers is equal to k squared. Now we want to show that if that's true, then pk plus 1 is true. We'll construct it by creating a sum of the first k plus 1 positive odd integers. Here's the first k positive odd integers. Here's the k plus first positive odd integers. If we consider the first k of them by the inductive hypothesis, we can replace that with k squared. And now I'll remind you that every time you're doing a proof by induction, you must use the inductive hypothesis somewhere in your proof. Well, k squared plus 2k plus 1 can be factored into k plus 1 squared, which is the result that we're looking for. That proves that pk plus 1 follows from pk, and so Pn is true for all positive integers n. All right, we don't only have to look at equations to prove to do proofs by induction. Here we'll do proof by induction for an inequality. The statement we want to prove is that n is less than 2 to the n for all positive integers n. So that's our proposition. Pn is n is less than 2 to the n. And the basis step, we're saying it's all positive integers, so our basis is 1. And 1 is less than 2 to the 1, so the basis step is proved. Okay, we're going to assume the inductive hypothesis, that is for k is less than 2 to the k in our inductive step. And we want to show pk plus 1. We're going to start by assuming the inductive hypothesis, and then we're going to add 1 to both sides. So here's our inductive hypothesis. Here we've added 1 to both sides. And now I'm going to replace this one with something larger than it, 2 to the k, since and continue that inequality. So k plus 1 is less than 2 to the k plus 2 to the k. Well, that equals 2 times 2 to the k, and then I can bring this exponent together to get k plus 1 is less than 2 to the k plus 1, which is pk plus 1 following from pk. Therefore, n is less than 2 to the n for all positive integers n. We don't have to only prove equalities or inequalities using induction. We can prove any proposition potentially at all that has a relationship to the positive integers. Here's an inequality that is, so we'll do one more inequality. Here's an inequality that will not start at the basis of n equal 1, but at n equal 4. That is, 2 to the n is less than n factorial for n greater than or equal to 4. So p at n is the proposition 2 to the n is less than n factorial. The basis step will be starting at 4, and that's true since 2 to the 4th is 16, 4 factorial is 24, so the basis case is proved. The inductive step, pk, will assume, and that is that 2 to the k is less than k factorial. We want to show pk plus 1 holds. So I'll just start with 2 raised to the k plus 1 power. That's equal to 2 times 2 to the k. I can go ahead and invoke the inductive hypothesis on 2 to the k, and that's going to give me that expression is less than 2 times k factorial. And now I can replace 2 with k plus 1, since I know it is greater than 2 and I want to maintain this direction of inequality. So 2 to the k plus 1 is less than k plus 1 times k factorial, but that equals k plus 1 factorial, and k plus 1 is proved. So Pn will be true for all integers n greater than 4. And note that P0, P1, P2, and P3 all happen to be false, so we had to start at 4. All right, one more proof by induction. This one is neither an equality nor an inequality, is a statement. And that is, we want to prove that n cubed minus n is divisible by 3 for every positive integer n. So Pn is our proposition, n cubed minus n is divisible by 3. Basis step starts at 1, and it's true since 1 cubed minus 1 is 0, and 0 is divisible by 3. It has remainder 0 when divided by 3, so it's true. Check. All right. Now the inductive step, we assume pk, that is k cubed minus k, is divisible by 3. And then we want to show that pk plus 1 follows. I'll make the expression k plus 1 cubed minus k plus 1, and then we'll go ahead and expand that cubed binomial to get k cubed minus 3 plus 3k squared plus 3k plus 1 minus k plus 1. The 1's will cancel out. We'll group this k3 with this negative k, and then we'll factor the 3's out of the other terms. And I get k cubed minus k plus 3 times k squared plus k. What can we say about that sum? Well, the first term, k cubed minus k, is divisible by 3 by the inductive hypothesis. How about the second term? Well, it has 3 as a factor, so it will also be divisible by 3. So I have two numbers that are both divisible by 3. That means their sum will be divisible by 3. What is their sum? Their sum is k plus 1 cubed minus k plus 1, which will thus be divisible by 3. And pk plus 1 is proved, and I can conclude that n cubed minus n is divisible by 3 for every positive integer n. That's a few more examples of doing proofs by induction. Remember, we always use the inductive hypothesis somewhere in the inductive step.